can we find a formula for the sum of squares visually? Let's find out. The number of cells in the square array shown here starts 1, 4, 9, 16, 25, and so on, so that the nth square s sub n is n times n, or n squared. We can build the sequence of partial sums of the squares as 1, 1 plus 4, 1 plus 4 plus 9, 1 plus 4 plus 9 plus 16, and so on. When we add these numbers up, we get the sequence 1, 5, 14, 30, 55, and so on. There are many visual proofs for the closed formula for this sequence, and you can find many of them on my channel linked in the description. It turns out that this sequence has a closed form given by n times n plus 1 times 2n plus 1, all divided by 6. But why stop there? Why not consider the sequence of partial sums of this sequence so that we have 1, 1 plus 5, 1 plus 5 plus 14, 1 plus 5 plus 14 plus 30, 1 plus 5 plus 14 plus 30 plus 55, and so on. When we compute these sums, we get a sequence starting 1, 6, 20, 50, 105, and so on. Is there a visual technique that can compute a closed form for this sequence? That is, can we find the formula for the sum where k ranges from 1 to n of the sum where I ranges from 1 to k of I squared? It turns out that we can find such a visual proof, and we'll use one of my favorite visual proofs for the sum of the squares formula to find this double sum. The visual proof for the sum of squares formula starts with a stack of squares representing the number 1 squared plus 2 squared plus 3 squared and so on up to n squared. Here we've pictured the case where n equals 4. Notice the squares are shaded to represent a classic visual proof that each square is the sum of odd numbers. From this visualization, we can lay down L-shaped gnomons so that we have one stack of size 2n minus 1, two stacks of size 2n minus 3, and so on, all the way down until we have n stacks of size 1 to create a tower that's shaped like this. But now we take two more copies of the sum of squares stack. One of them we flip upside down and place on the left of the tower. The other one we take a mirror copy, flip it upside down and place it on the right side of the tower. Using three copies of the sum of squares provided us with this rectangular diagram. This rectangle has a width given by 2n plus 1 and a length given by the sum of the first n positive integers. This means that 3 times the sum of the first n squares is equal to the sum of the first n positive integers times 2n plus 1. Using the well-known formula for the sum of the first n positive integers, we see that the sum of the first n positive squares is equal to n times n plus 1 times 2n plus 1 divided by 6. More importantly, we see that this diagram shown here will be a nice visual representation of 3 times the sum of the first n positive squares. And we'll use this visual representation to find our double sum. In particular, to represent the quantity 3 times the sum where k ranges from 1 to n of the sum where I ranges from 1 to k of I squared, we can consider 3 times the sum of the first 1 squares, plus 3 times the sum of the first 2 squares, plus 3 times the sum of the first 3 squares, and so on, up to the quantity 3 times the sum of the first n squares, each represented by a diagram from the previous visual proof. But then these diagrams can be rearranged nicely as follows. Take the first one and place it here, rotate the second one and place it underneath, place the next one to the right, and keep this process going, each time either placing the diagrams next to each other or rotating and placing them next to each other. This process will result in a rectangular array of cells, with the width given by the sum of the first n positive integers, and the length given by the sum of the first n minus 1 positive integers plus 2n plus 1. Notice that 2n plus 1 is equal to n times n plus 1. So the length of this rectangular diagram is actually the sum of the first n plus 1 positive integers. By applying the sum of integers formula, we see that this rectangular diagram has a width of n times n plus 1 over 2 and a length of n plus 1 times n plus 2 over 2. So we conclude that 3 times the double sum of interest is equal to n times n plus 1 over 2 times n plus 1 times n plus 2 over 2. Therefore, from all of this, we see that 3 times the sum where k ranges from 1 to n of the sum where I ranges from 1 to k of I squared is n times n plus 1 squared times n plus 2 all divided by 4. When we divide both sides by 3, we get our formula for the sequence of partial sums of the sum of squares. In particular, the closed formula for this partial sum is given by n times n plus 1 squared times n plus 2 all divided by 12. We used a famous visual proof for the sum of squares formula to find a visual proof for the sum of the squares formula. This visual proof is attributed to C.G. Waston by Roger B. Nelson in his second Proofs Without Words compendium. You can find a link to that resource in the description below.